Okay, so this problem, it says suppose f has a continuous derivative whose values are given in the following table. The first question says estimate the x-coordinates of the critical points of f for x being between 0 and 10. Well, remember that the function has critical points where the first derivative is either 0 or undefined. Well, here it says that the derivative is continuous, and these are the values, so all we're looking for is approximately where the first derivative is 0. And so if you take a look at these, well, here it gives you the x values. X equals 0, x equals 1, x equals 2, x equals 3. And if we're looking for where the derivative is equal to 0, well, here it goes from 1 to negative 2, so it goes from positive to negative. That means that when x is approximately equal to somewhere between 2 and 3, well, let's just say 2.5, you're going to have a critical point. Okay, and then here it's negative, negative, and then now all of a sudden it becomes positive right here. Well, this would also be a critical point, right? Somewhere along the lines of 6.5. And if you keep looking, well, here it goes from positive to negative again. So this is also a critical point. So there's 3 critical points between 9 and 10, one between 6 and 7, one between 2 and 3. And we just approximate those as 2.5, 6.5, and 9.5. Okay, and then if we want to know whether it's a local maximum or a local minimum, well, remember that the first derivative tells you whether your function is increasing or decreasing. So remember that if the first derivative is positive, then your function is going to be increasing. If the first derivative is negative, then the original function is going to be decreasing. And so what that tells me is that if you take a look at here, why don't we put little arrows that tell us whether the function is increasing or decreasing. When x is equal to 0, since the derivative is positive, it's going to be increasing. When x is equal to 1, the first derivative is positive, so it's going to be increasing. Again, the derivative is positive, so it's going to be increasing, sorry. And then when x is equal to 3, the derivative is negative, now it's decreasing. This means that this value, when x is equal to 2.5, when x is about 2.5, we have, since it's increasing and then decreasing, I'm going to have a local maximum. Okay, now if we continue this little analysis, when x is equal to 4, it's going to be decreasing. When x is equal to 5, it's going to be decreasing. When x is equal to 6, it's going to be decreasing. But now when it's equal to 7, it's going to be increasing. So this would be when x is approximately 6.5, we're going to have a local minimum because it's decreasing and then it's increasing. And I'm sure you could probably guess by now the next one, increasing and then decreasing. This tells us that it's a local maximum as well. So when x is about 9.5, we have a local maximum. And that's it. Okay, so in this problem we're trying to figure out which one is the function, the first derivative, and the second derivative. And the easiest way to tell is by taking a look, remembering what the let me zoom in on this one first, actually. If you take a look at where the original function has flat spots, you know that its derivative has to equal 0 there. So, for example, take a look at this flat spot right here. This one has. Notice that, so this is A. A has a flat spot here, here, and here. So its derivative would have to equal 0 at each one of those spots. So notice that B is equal to 0 here, but it's not equal to 0 right here. So B can't be the derivative of A. That wouldn't make sense. Okay, now let's take a look at C. Well, C has a flat spot right here, and B is 0 right there. And that's the only place where it's equal to 0. And so that looks like it works. If maybe C is the original function, and then B would be its derivative. Now let's take a look. Let's see if A is the derivative of B. Well, B has a flat spot here and here, and then A is equal to 0 here and here. And so those match up. So that means C would be the original function, B would be the first derivative, and then A would be the second derivative. This goes against the original, the commonly misconceived notion that the derivative always has less, we'll call them squiggles, than the original function. That analysis only works for polynomials, not for every single kind of function. Okay, so let's do the other one. Okay, so if we apply the same line of thinking that we applied to the previous problem, let's take a look at the flat spots of each function. So if we take a look at A has a flat spot right here, and then it has a flat spot right here. And if we try to match it up with the zeros of another function, notice that it matches up with C here and here. So that's good. But what about B? Well, B has a flat spot right here, and A has a flat spot right there. I mean a 0 right here, so those match up. And then B, it's kind of hard to see, but it has a flat spot right here, matches up with A. So, well, if you you apply that reasoning, it looks like the derivative of B is A, so this would be the original function. And then the derivative of A is C, so A would be the first derivative, and then C would be the second derivative. And that's it. And this one looks more like a polynomial. So if you look at the squiggles on this one, though, as opposed to the last one, this B has 1, 2, 3 on that you can see. A has 2, and then C has 2 as well, but there might be other squiggles over here that you can't really see. So that's why you got to be careful when you make the when you just look at the squiggles. You want to look at the critical points. That's the better way to tell.